waiting, I can share just to make sure those things are. I can check whether. I mean, I'm an assistant professor at Princeton, and I co-lead the Princeton NLP group. And today, I thought I'll talk about some of our work, which has been revolving around. Sorry, I just hear some music from somewhere. I just want to make sure it's not me. Okay, better. Yeah. So today, I just wanted to present some of our recent work and make the case for how we can use natural language processing to help reinforcement learning. So let me jump in, right? So I'm sure, many of you, especially the first left-hand figure here, must be very, very familiar to many of you. So, a few years ago, DeepMind had this reinforcement learning agent. Google DeepMind had this reinforcement learning agent that could defeat the human champion, Lee Sedol, at Go, right? So we've really seen over the last few years considerable success in scaling up reinforcement learning algorithms and applying them to many large state spaces and challenging games like Go or Dota. This was some work that OpenAI had a couple of years ago, and the nice part is these agents can now beat human players, which is very, very impressive. But at the same time, they require lots and lots of training. So for instance, this 45,000 years of training is what you would require to train an agent to play the game of Dota, which is quite a lot, right? Like human players, they pick up a game very, very quickly. And that's much more than any human can ever get in terms of experience. So that's what we have on reinforcement learning on one side. On the other side, we also have had applications of reinforcement learning to natural language processing, right? So if you want to build your own dialogue system, systems that can converse with humans and things like Alexa, Siri, you would need some form of interaction with humans and using language. So reinforcement learning has been applied to cases like that, and even cases like robotic instruction and so on. So when you want to let's say instruct robots, let's say you have a house cleaning robot, you want to instruct it to clean your house and so on, you can do that. So basically RL has had a lot of success over the last few years, but two shortcomings that we are seeing is the fact that sample efficiency of these algorithms is very, very bad. So what I mean by sample efficiency is you need so much training of these algorithms. 45,000 years is a lot in order to train these agents. And at the same time, if generalizability of these algorithms is very, very weak. So let's say I train an agent to play Go. I can't automatically expect it to play chess, right? Even though as a human, you would probably have certain strategies that could help you, like just the notion of attack, defense, things like that, right? So these are two weak points that we have in current RL algorithms. And what I want to do in this talk is to tell you and give you ideas as to how we can use language understanding to help reinforcement learning. Okay, so the idea behind this is basically to say that we can, just like how humans learn from both interacting with the world as well as reading books, right? In a similar fashion, we can develop agents that can read information in the form of text, and at the same time be able to interact with the world in many different ways and learn from both of these sources. So basically, what this could be useful for is, first of all, we can now probably have agents that can achieve multiple tasks and goals, right? Instead of training an agent just for Go, maybe we can train agents for playing a wide variety of games, right? Moving towards more and more general forms of intelligence. I'll show you how, we can also use these kind of techniques to transfer policies between environments for faster learning. So if I have an agent that has learned to play Go, I can show you how we can immediately transfer it to play a different game, right? And another advantage that I'll show you is, we can also make use of language, natural language, be it English or Korean, to sort of train agents in more flexible ways. So in reinforcement learning, there's this notion of training from rewards, but I'll show you how we can train using more general abstract structures. So specifically, you know, I'll talk about 3 different parts. So, and you know, I'll sort of stop after each part to ask if there's questions and so on. But the idea is I'll show you how we can use natural language to, by the way, can you see my mouse or? Okay, great, thanks. Yeah, so I'll show you how we can use natural language to represent actions in a reinforcement learning setup, dynamics in a reinforcement learning setup, and as well as rewards in reinforcement learning setup. The reasons for why we want to use language are, of course, like, first of all, it's easy to get from humans, right? So you and me, we are very, very proficient at communicating in language. And that's going to be a huge advantage as opposed to, you know, going in engineering reward functions, engineering environments, and so on. And the second reason is basically we can use language to sort of provide more semantic structure, right? So when you or I, as humans, when we are thinking about playing these games or, you know, operating in different environments, we naturally build some semantic structure in our minds, right? Like how a table stands on the floor, how something stands on the table, things like that. So I can show you how language can also provide this sort of natural space for exploring this semantic structure. So any questions at this point? Sorry, just want to make sure like this is at the right level. People are on board. Okay, awesome. Sorry. Was there a question? So rewards is basically, I'll show you an example, right? So I'll answer that with an example. So here's an example, right? So are people familiar with the game of Dota? Nod if you are, maybe, or maybe not. Okay, right. So I'll explain it maybe with this game, right? So Dota is this game where you control, you play, it's a team game, but you basically control some entities that are called heroes, okay? And there are, you know, AI bots, which are called creeps, right? So the computer controls these. And so the objective of this game is to basically, you know, you start off, let's say at this corner here, and you slowly want to build your way to sort of end at this point and destroy the enemy's base, right? So you play against an opponent, and the idea is like you know, you sort of have to keep fighting, and keep going till you reach the enemy's base and destroy the enemy's base, right? So if I were to train a computer to play this game, right? So how I would train it is I will first, you know, give it all information about the game, right? And allow it to take actions. So the action can be like move forward, you know, attack the creep, or like, you know, upgrade your items, do all sorts of things. And then I can then provide the agent rewards to be able to train it with reinforcement learning. So rewards are basically scalar values. So whenever, think of it just like a carrot and stick kind of example. So if you do a good thing, I provide you a positive reward. If you do a bad thing, I will give you a negative reward. So based on this kind of feedback, the agent can learn which actions are good. So for instance, defeating opponents is a good action. Dying is a bad action, right? Like bad state to be in, basically. So this reward-based learning is basically trying to make sure that, you know, you get the agent to maximize rewards, which means winning the game in some sense. So in other sense, you can think of like, you know, where in certain games you have this like game score, like if you're playing these Atari games or things like that, you have the scores. The score can be a reward in some sense. You want to maximize your score in the game, for instance. Did that make sense?
Thank you very much for, yeah.
Sure.
Thank you very much for my for asking.
No, this is totally fine. I think this is going to come up again and again, even in the stuff we see about rewards. So it's a great question. So this is the game of Dota, right? So, and what I meant was, I showed you one variant, which is the main game of Dota, right? So now let's say we have trained an agent to play the game of Dota, right? So this is what OpenAI did actually in 2017, actually. And they beat the world champions at Dota. So now let's just do this thought experiment, right? So now if I change the goal of the game itself, so I said, like I said, remember the goal of the original game is to go to this end here and destroy the enemy's base or castle or something like that. And if you change the goal and say, okay, capture the flag, like go to that place, capture a flag, and then come back to yours, that changes the game completely. But the Dota bot that has been trained cannot actually adapt to this new game, right? Without having to train again for 45,000 years of compute experience. Similarly, you know, if I change even something like the dynamics, right? Like if I now make a variant of the game that says, if you die, you cannot respawn, that changes the game completely also. And I could also change things like actions, right? So now there's no action in the original game that allows you to jump, but let's say I provide you a single action that allows you to jump. You know, as a human, you will have no problem, right? Like you will have no problem adapting your knowledge of this game to any of these variations that I'm talking about, because you understand what I mean, right? Like if I say, hey, I give you a new action that allows you to jump, you'll immediately understand what it is and try to use it in your gameplay, right? The rest of your strategy remains the same. But our current agents cannot do this, right? And so what I'll show you is like some steps towards getting our current agents to use these kinds of information in generalizing their policies to new environments. Okay, so I'll start off with part one, I guess. So this is the part where I talked about, I'll talk about how we can use language understanding for actions. So here's an example of some work we had in 2015. So has any of you ever played these text-based games, like text adventure games? These are old games before we had, you know, like graphics engines or, you know, all of these. So this is how some of these games look like. So, you know, like back when we had terminals and, you know, you had to type everything in. So these kind of games are very interesting because everything is in language. Everything is in natural language, just text. So as a player, right? So you can get a sort of prompt like this. You are standing in an open field west of a White House with a boarded front door. There is a small mailbox here, right? And so it's your adventure, right? You can type in anything you want and the game will move on and you can do different sorts of things. So maybe you can say, you know, open mailbox. You can maybe say go east. You can say open door. And all of these are available actions, right? So as you can see, you know, this is in text. The state is in text. The actions that you can take, any one of these actions, is also in text, right? So these sort of environments provide a very nice test bed for developing RL algorithms that learn the semantics of actions through language, right? So as a human, for you, this action makes sense because, you know, open door, this action makes sense because you know there is a front door that is closed, right? You're not going to randomly say eat egg or something like that, right? So you have an understanding of like what makes sense in this context. You're going to use that to you know, try different actions in the game itself. So this basically provides us a sort of like an environment. So you can think of this as like, you know, like just like we have Atari games where, you know, you see a visual screen and you do some actions, you move around and things like that. This is just like text game. So everything is in text. You have to understand the text and then reply in text, and then the game moves on. So you can see that why this can be challenging for our machines, right? Like as humans, it's very easy for us. We can understand the text, but machines really have a hard time to understand this text. So they need to have very good representations for language in order to solve these kind of games. So back in 2015, right? So we had a simple model to sort of do these things. So what we had was a model called the LSTM DQN, which is basically, are you guys familiar with like LSTMs and DQN and so on? To some extent?
No.
No, okay. So you can think of the LSTM as basically a neural network, right? It's a recurrent neural network, and it's used to process text. So if you have a sequence of words, you know, you can sort of feed this through the neural network, and it gives you a vector. And we basically use that to sort of process these different types of states, basically. So we feed this state into a neural network, and then the neural network would just then generate one of these actions that are then fed into the game. And then we would use reinforcement learning basically to learn representations on the fly to play these kind of games. So you can see here that our model compared to several different baselines does much better in that it's able to solve these kind of games, at least at one particular game, to around 98% accuracy. Like this was one game. You can, of course, read the paper for more details. And so this was obviously like the solving the game is one thing, but here's the interesting part, right? So if you look at this graph here, this is basically, you know, a visualization of word vectors that were learned by the agent, right? So these are all words that appear in the game, okay? And the agent learned some vectors for all of these games. Okay, this is the neural network. The neural network is learning the vectors for these games. And so what happens is we just clustered them basically, or did some form of, so TSNE is some form of, let's say, dimensionality reduction and clustering. So the interesting part is, you know, just from playing the game, right? The agent has no idea of language before playing the game, but you can see after playing the game, it learns to put words that are very, very similar together, right? So you have words like pizza, fridge, kitchen, Coke, ice cream, things like that, that are very, very close together, you know, and then grass, plants, trees, and so on, that are very, very close together. So basically the agent, just by playing the game, is learning to understand language, right? So you can think of how you would do the same thing, right? Like let's say I wanted to learn Korean, for instance, right? If I play a game like this in Korean, you know, I would slowly learn to associate things. You know, maybe this was in Korean, but then I understand, okay, maybe this particular symbol means like a door. I will keep trying different things and so on, but then just learn from my game score, right? So if I'm making progress in the game, hopefully I understand more and more of the language itself. So this was sort of like a demonstration of that we had back in 2015. So basically showing that current RL techniques can learn language just by interacting in an environment. Okay, so I sort of gave you a pitch for why these games are useful anyway, so I won't go over this again. But one interesting thing that has happened since 2015 is that a lot of people have started working on these text-based games, okay? So there's actually a workshop happening in this year's NeurIPS also on this, and it has happened before also. So like I said, you know, these sort of games are very nice because they provide a way of performing reinforcement learning on a purely textual environment, okay? And like I said, you can learn language, you can learn other things and so on. But what I've noticed is that, you know, most of these efforts, they only focus on doing reinforcement learning, right? So they basically treat these games as just another kind of game, right? Like just like AlphaGo, like just like chess, just like Atari, they're just treating them as another form of games and using reinforcement learning to sort of, you know, train policies for this kind of a game. But what I want to say is that, you know, that's actually fine, but we're really missing out on a lot of information, right? So if you look at this particular example, two different games, right? You can see that there's a variety of information that's provided in the text. And if you just feed it into a neural network without really considering how these, the meaning of the text, then, you know, you're not really leveraging the fact that there's a lot of semantics in this and that can be used in developing better agents, right? So basically what I'm trying to say is like, this is not like Go or chess, because a lot of the meaning of the game itself is present in the text. You just have to read it to figure out. So, all right, so to sort of give you a better sense of this, right? So here's how a very typical approach to solving these games looks like, right? So like I said, this is a game, right? So what happens is you feed this kind of text into a neural network. So this is a typical neural network. It's called the DRRN. Back in 2016, He et al. Had this network. So these GRUs are basically like the LSTM that I mentioned. They're just recurrent neural networks, and they process the text. So you feed in the text through all of these three different things. Like, I mean, this this is the inventory, there's a description, and this is the other part of the state, and so on. And over here, you feed in actions, right? So you feed in an action like move rug, right? Goes through the GRU, you get some vectors, and at the end of the day, basically you get some Q values which tell you whether that's a good action to perform in that state or not, right? And that's what is trained through reinforcement learning. So what we showed, so this is actually appearing in a workshop this year, and was led by my student, Shunyu Yao. So what we showed in this work was we wanted to see how much of this text the model is actually understanding if we simply do reinforcement learning, right? So what we did was to do some very, very simple unit test kind of setting, right? So what we did was, instead of having the full representation like this paragraph, right, which gives you all the information of the game, we replaced it by just using a location phrase, right? So instead of that whole paragraph, you'll just get that a phrase that says you're in the living room, right? That's one variation. And the other variation that we did was to say, okay, we're simply going to hash all the states. So, you just use a hash function, feed in this entire text into the hash function, and you get a hash. This is literally a hash, right? So as a human, this is not at all interpretable to us. As a human, this is somewhat interpretable to us, but again, it's not enough information for you to actually know what's happening, right? So our hypothesis was that, if any of these two models do as well as this full model, then that means that this model is not really understanding language, right? It's just treating them as a bunch of symbols and just, learning some representation which doesn't really have semantics. So here are some results, right? So this is what, these are a bunch of games from a benchmark called Jericho, which was introduced by Microsoft Research a couple of years ago. So as you can see, this has many, many different games, right? And it's a very nice benchmark, by the way, if any of you is interested in using it. It's a very nice benchmark where you can, have these different games and try them and so on. So the full model here gets a normalized score of 21%, okay? And then when we have the min observation model, you can see that the performance drops, right? So the reason the performance drops is because the information is much, much less, right? So we only give it the location information, and you can see how it drops to around like 12%. But surprisingly, the hash model actually gets a higher score than the neural network, right? So it's basically saying a simple hashing mechanism is doing as well or better than a neural network. That means that the neural network is not really learning a good language model, right? It's not really learning something that's representative for the language itself. So, I mean, we have some hypotheses as to like why hashing could help. One of the hypotheses we have is like, so these are basically, different states in the game itself that are plotted according to their representations from the base DRRN, the neural network, and this is just the hashing model. And you see, one of the reasons it's probably likely that the hash model does well is because the states are very, very discriminative, right? So the hash model is able to say that this particular state is different from this state and so on. So there's no repetition of the dots. They're not overlapping with each other. So whereas the DRRN base model has this problem of not being able to perform state aliasing, it's not able to tell, if you're in the living room with an apple versus if you're in the living room with an orange, it's not able to tell the difference, for instance, right? So basically, this tells us that the current models that we have don't really have a good understanding of language. So what should we do, right, based on this knowledge that we have, right? So our job, I mean, at least some of the work that I'll present now, is to basically make use of this rich variety of information present in text, right? So there's a lot of different things like actions, observations, guidance, and feedback that you can get from the text itself. And I'll show you how we can develop new techniques that build upon the basics of reinforcement learning to make agents that can read and understand things, right? So some of this work that I'll talk about is on these text-based games. but some of this will also be on more general environments like robotics and so on. Okay. Any questions? Like, is this fine in terms of the pace? Should I go faster, slower? I don't know. Just want to get a sense of what folks are thinking. Okay.
Yeah, so far,
all right.
good. Yeah.
All right, cool, thanks. So I'll start with, understanding for actions, right? So what do I mean by understanding for actions? So here's an example just to sort of illustrate the intuition, right? So we have two actions in this game, that game example that you see. One is go south and one is go east, right? And as soon as you see this, right, for you, it's obvious that these actions are related, right? So there's some compositionality in the way that these commands are generated, right? So both of these actions are about going somewhere, right? So that's how they're related, except, the direction changes, right? So we don't want to really represent them as just like two different integers in some action space. So to sort of be more specific, right? So most of these games have action spaces that are very, very huge if we simply treat them as independent symbols, right? So given the complexity of these kind of games, right? Like you can construct many different commands. In fact, some of these games, you can have more than 240 billion actions that you can just generate, right? This is just because, you can have a vocabulary of, a few thousands. And then, if you have a command that's like four-word command, you can just see the combinatorics, right? You just multiply and the combinatorics gets really huge. So our approach here was to say that, okay, we're not going to do the standard thing that people do in Atari games or Go or chess, right? So instead of just treating all of these actions as independent and different, what we're going to do is like, we're going to leverage the fact that these actions are all in language. We're going to leverage language semantics to enable a better exploration of action space, okay? So to sort of give you an intuitive sense, right? Like imagine you get this kind of an observation, okay? You're in the living room, you see all of this, right? These are some examples of random actions, right? So if I just take the vocabulary, randomly generate a sample action, I can say something like close door, north A, which is not even grammatical, right? I can say eat troll with egg, which maybe in some weird sense is grammatical, but obviously it's nonsensical, right? No human, I mean, at least I hope you wouldn't want to try an action like eat troll with egg, right? If you're in this kind of a scenario. So what we want to do is like, we want to develop agents that, use their common sense reasoning to say, okay, I'm not going to try actions like eat troll with egg because it doesn't make sense from a common sense standpoint. We also want to make agents that, maybe explore contextually meaningful actions, right? So if the agent is in a dark room, maybe the agent should think, okay, I need some light to see things, right? So it should try to perform an action like turn on lantern, okay? So that's sort of like our goal. So what we do, what we basically want is a good prior for action selection, right? So we want to give the agent some sort of game sense, some sort of common sense to sort of tell the agent what are good priors to sort of explore, right? Remember, the agent is still trying to learn. It doesn't know what to do specifically to win the game. It's just exploring from the beginning, but you can still have some common sense to explore in a smart way, right? So what we did here was we trained a single language model on human gameplay. So what we did was we basically took some data that looked at how humans played these games, right? So you have these transcripts of people playing this game that we scraped from the web. These games, not a particular game, many different games. And then we trained, a language model. Have people heard of GPT-2? Or no? Okay. So GPT-2 is this, very large language model from OpenAI that can actually generate pretty cool sort of text, right? So actually, maybe I should just show you this. Let's see. Oops. Okay, I'm not able to. Can you see my browser? Hello, can you see my browser? Sorry, just want to check. Oh, okay, yeah. Right, okay. So here's an example of GPT-2. So this is basically a language model, okay? So let's say I type in something like, this is a sentence I want to, and then press tab. So, you know, this is a completion from the language model. So basically, given this premise, the language model basically has completed this entire, you know, sentence and sort of, you know, wrote down the next part of the next sentence also. So basically, it's a very, very powerful language model that can complete text, right? So if you want to generate your own story, feel free to, you know, play around with this kind of a demo. Right. So with that context, right? Like, so basically, what we did was, you know, we trained the GPT-2 kind of language model to take in this whole observation as input and try to generate potential actions that might be useful to explore. Okay, so this is basically sort of providing it some sort of common sense in order to play these kind of games. So this was also work led by my students Shini Yao and Rohan Rao, and you know, you can there's a paper in EMNLP 2020 if you want to see more details. So the idea is basically, you know, we want to generate these different actions, and then we want to use reinforcement learning to re-rank, right? So all of these actions are plausible; they're good actions for exploration, but we still want to know which actions are good, are the most optimal for a particular case, right? So in this case, the most optimal action is move rug, but an RL agent will try to learn and figure out what's the most optimal action for a particular game. So yeah, so just to give you a sense of like how this would look. So, you know, most of the previous approaches, what they would do is like, this is the reinforcement learning agent. This is the game engine here. So the game engine will provide an observation to the reinforcement learning agent. You know, reinforcement learning agent would take an action. But the problem is, you know, since the number of actions is huge, right? So most people would use some sort of handicap to sort of cheat in some sense, you know, take the underlying game state and use that to just give a smaller list of admissible actions to the RL agent, right? So but instead, in our model that we call CALM, right? This is our model CALM. What this CALM model is going to do is it's going to remove this dependence on, you know, this handicap that you need, right? And all it's going to do is like from the game engine, you take the observation, it's going to produce a bunch of candidate actions. And then the RL agent is basically going to be the same. So we basically sort of added in a language model to generate these actions, which can then be used by any RL agent. So in this case, we use an RL agent that's called the DRRN, again, the agent that I showed you, but you can potentially use this with any agent that you want. And it sort of gives you a good common sense prior for playing these kind of games. Right, okay. So how do we train the CALM? Like I mentioned before, we sort of use these human gameplay trajectories. So these are basically, you know, sequences of observation, action, and so on, like the ones that I showed you. And the idea is like, we can just train these language models like the one that I showed you, GPT-2, using a standard cross entropy loss on the action token. So the idea is like, given a particular context C, right, like the words that are there in the context, you want to predict what action you want to take and maximize this with some kind of a cross entropy loss. So we also consider a very simpler model, like this is called the n-gram model, which is only based on action n-grams. So it looks at the previous actions and tries to figure out what the next action could be. But this is a very much simpler model. But I think for you know, purposes of this talk, you can just focus on the GPT-2 model because that's the main one that that we want to sort of use. So how do we use CALM in RL? Like I mentioned before, so given a context C, we just use our CALM model, which by the way is very general. You can use this on any sort of game. So we just train it first on one offline data set, and that's it. We don't have to train it anymore. you can use it to produce top K action candidates for any of these types of games. And importantly, COM is not fine-tuned on the game, right? So it's just a generic language model that imparts some common sense game knowledge. So we then use RL to train the action re-ranker that helps maximize the game performance. And again, the rationale here is like we want to make COM as general as possible, whereas the RL agent should be more and more specific to a game. So yeah, these are the data sets that we use. So again, the Jericho benchmark is what we use to test the RL agent. So this is the data set released by Microsoft. There's 28 different games with similarity access and these action handicaps which people use. And for the Clopfloyd data set, we used, we scraped some 590 games that people played. These are all, remember that these are all human players, so they're not optimal walkthroughs. They're not optimal trajectories. They're not giving you the answer to this or the best moves to make in any situation. They're just like noisy, non-optimal actions that people take. But the important part is they give us an idea of common sense, right? What do people think they should do in a particular scenario, right? And I think that's the sort of intuition and knowledge we want to impart into COM and use that in the RL agent training. So basically think of this as like, you have a game playing agent that has sort of seen what people do in certain situations. It learns what are common sense type of actions, and then it goes and plays its own game, and then tries to use that common sense in trying to, explore and try different actions in order to learn to optimize for that game. So the important thing is here is like we made sure there's no overlapping games. So we're not training on testing on the same game at all. So we evaluated COM along with a bunch of different baselines. So again, these are probably too detailed. You can look at it in more detail if you want. So NAIL is only the previous baseline on this kind of a task, which does not use any handicap. There are two other models which actually require that handicap that I talked to you about, like the handicap where you have to get access to the underlying simulator and use the ground truth action values and provide that as choices. So these blue models are basically they're not really fair comparison with what I'm going to show you with our model, but I'll still show you how well they do and how well we do. And here are sort of the results. So the NAIL model is the previous sort of state of the art without any handicap. And you can see it gets a normalized score of like 5.6%. So it's able to solve only 6% of these games on average. And this is averaged over all 28 games. So some games are very hard, some games are very easy. So this is an average score, which is quite low. And you can see our model COM with the GPT-2 has quite a big boost, gets around 9.4%. And surprisingly, it's almost the same as a very sophisticated model that uses this action handicap and other sort of ground truth validation to do this kind of games. And importantly, I think we noticed on around 8 out of 28 games, we actually outperform these models too. So without having that prior knowledge, without having that handicap, we can do much better than even models that have that handicap, just because we have imparted the agent with an understanding of language. I'll skip this because it's more detail in terms of like, some analysis, some ablation studies that we performed on the data. I'll stop there. Like, were there any questions about COM in general? Does that give you a sense of like how, if you impart models of an understanding of how actions play a role in a more semantic sense, that gives you a better performance? I don't know. If anyone had questions, I can take them here, or I can keep going.
Okay, I have a question.
Right. Good.
In this natural language learning model, how many trainings are required?
Great question. So we used these many samples to train the model. So it's like 200,000 pieces of text. So 200, when I say sample, a sample is basically something like this. So it has one state and one set of actions. So if we have 200K, I think we collected around 200K of these to train the model.
Oh.
So
thank you very much.
Yeah, one thing is that this is a pre-trained GPT model that's fine-tuned for these games. So the GPT-2 model itself was trained on much, much larger data. So it's like trained on web text. So you take a lot of data from the web itself and train that model. Okay, cool. So let me move on to dynamics, right? So I